and welcome. Today we'll be doing question 1 out of chapter 1 of gunning, which says to write out the proofs of equations 1.4 and 1.8. Equations 1.4 are given here, and 1.8 are given here. Take a few seconds to try this out for yourself, and then you get some hints, and then we'll move on with the proof. Alright, for some hints, for 1.4, try to consider each of these sets in words in order to prove it. And for questions 1.8 or equations 1.8, to prove that two sets are equal, you should show that the two sets are subsets of one another. Since if two subsets are subsets of each other, then they must be equal sets. Alrighty then, with those hints, let's start with equations 1.4. These are De Morgan's identities, which are often written without the ambient set A, but for now let's keep them. So, to prove this, let's consider elements in this. A excluding B union C. So we can draw ourselves a little picture. We'll call this set A, here's B, and here's C. So if we describe this in words as per the hint, we see that these are all the elements in A that are not in the union of B with C. However, the union of elements B with C is just a set of elements that are in B or C. But if A is all those elements that are not in that set, those are all the elements that are not in B or not in C. However, we'll note that that's identically the same as those elements that are not in B and those elements that are not in C. Since, consider consider a contradiction here. Suppose that there were some elements in that other set, then you develop a contradiction. So we see the set of all elements that are not in B or C are all the elements that are not in B and all the elements that are not in A. So we can write that mathematically as A except for B intersected with A except for C, and you can see that graphically as well. Likewise, if we want to try the same trick for the next one, we consider all those elements that are in A and that are not in B and C. But those are all just not the elements that are in B and C. So those are all the elements that could be in B or could be in C but are not in both, and all the elements that are in A. So everything that's in that could be in C and A but are not in B are namely A except for B, and all elements that could be in B or the rest of A are A except for C. So if you consider the unions of both those, you exclude exclusively those elements that are not in B and not in C. Another way of phrasing that is all the elements that are not in B and C are those elements that are either in B or in C. So it's the union of all those elements that are not in B with all those elements that are not in C. Because all those elements that are not in B are all the elements that are exclusively in C. And since all those elements that are not in C are those that are exclusively in B. So if you union those as well as with the rest of the set A, excluding the union of B and C, then you get the correct set, which is exactly what the set on the right represents. It may be worthwhile to write this out for yourself. Next, let's try equations 1.8. Starting with the first, to see if these are the same, we will first prove that the left-hand side is a subset of the right-hand side, and then that the right-hand side is a subset of the left-hand side. In particular, let's start with left as a subset of the right. Let's consider some element little x in the union of x1 and x2. Well, that element x is either in x1 or in x2. So we take f of that x. We're either in f of x1 or f of x2, which you can represent as f of x1 union with f of x2. Therefore, we see that f of x1 union x2 is a subset of f of x1 union f of x2. Let's now prove the reverse direction. Let's suppose you have some element in either the image of x1 or the image of x2. Well, that's going to be a subset of the image of x1 union x2. This is because we consider some y in this union. Well, either it's in x1 or it's in the image of x1, or it's in the image of x2. But that means it's going to be in the image of, for sure going to be in the image of both the union x1 and x2. Therefore, we have the subset in the reverse direction, and we're done. Next, let's try the second one. We're going to proceed in the exact same way, but the reason we're going to have the proper subset is we will see that the reverse subset inclusion does not apply. That is, let's consider some little x in the intersection of x1 and x2. Well, it has to be in x1 and x2 simultaneously, so let's consider something as an image. Well, that clearly has to be in the image of both x1 and x2. So we can write that as the intersection of the image of x1 and the image of x2. However, we see the reverse inclusion does not hold, because if we consider some elements in the subset in the intersection of f of x1 and f of x2, let's consider some x in x1 that is not also in x2, that is in the image of f of x1, but is not in the image of x1 intersects with x2. Therefore, we have an element that is in the left set, that is in the right set, but is not in the left set. Therefore, the right set is not a subset of the left set. Therefore, we have the second equation here. Let's continue with the next one. Let's consider the pre-image of the union of two sets. That is, if we consider some y in y1 union y2, then it's either in y1 or y2. So if we consider its pre-image, the pre-image is clearly going to be a subset of f inverse of y1, or it's going to be in the pre-image of y2. So it's going to be within f inverse of y1 or f inverse of y2, namely f inverse of y1 unioned with f inverse of y2. So we have subsets in one direction, namely we have this subset. Alternatively, let's prove the reverse direction. If we have some element that is in this union, some element that is in f inverse of y1 unioned with f inverse of y2, then it must necessarily be in f inverse of y1 union y2. Therefore, we have the reversed inclusion. And with both directions inclusions, we're done. You should try to convince yourself why this is true. Finally, repeat the exact same explanation for this one, except we will note that since we're using pre-image, we have a more well-defined mapping, so we get the reverse inclusion, and let's explain that now. The forward direction inclusion from left being a subset of the right is easy, and it kind of follows as before. Now let's consider the reverse inclusion from the right inside the left. Let's consider some element in the pre-image of y1 intersects with the pre-image of y2. Well, if it's in both of those, then it has to be in the pre-image of y1 intersects with y2, since we're considering pre-images here. That is the set of all elements that will be set to y1 and will be sent to y2. That is, we have some xi that is in both the pre-image of y1 and the pre-image of y2. Well, since the pre-image of y1 and the pre-image of y2, that means it's going to be in the pre-image of y1 and y2. Since if it's in both of those, then when we apply the pre-image operation to it, it's going to be in the pre-image of y1 and y2, since that's the only way it's possible for it to be in the intersection of, or in the pre-image of both of them. Consider that further, and we'll see that these proofs get a lot easier as we go on because they become more formal, as opposed to having to consider sets in this way. Thank you.